I dive in with my own.
If I could ask a second question, I wanted to ask Serena one more question about her talk, if it's not too late.
No, that's the whole point.
Me.
Okay, yeah, I didn't want to hog the microphone. So I'm just, the slide you have up right now seems to suggest that, from a spectral standpoint, finding the Uralites is hard. Is there anything in there that, or I guess, is there anything diagnostic that we'd be able to use if we wanted to search, like if we wanted to go to a Uralite body or a Uralite near-Earth object or something like that? Is there anything diagnostic in what you're finding that would help us sift out those bodies from everything else?
The answer is we haven't done anywhere near enough experiments to know any solid answer to that. I'm hoping that we will be able to do so. But the key, I think that the key to the whole thing is to think about what kinds, excuse me, I gotta get the cat out of the way here. Okay, cat's been evicted again. The key is to think about what kind of uralitic asteroid you might find out there. And there are basically two things. There's either something that has sat around for a long time, long enough to develop uralitic regolith on it, like I think 2008 TC3 was a piece of, or it's a newly excavated mantle piece. Certainly there are newly excavated mantle pieces out there because we get uralites coming to Earth. And think about looking at those two materials separately. So I think if we start, there's a whole lot of petrologic variation amongst uralites, and it's kind of bewildering to think, how do I start trying to find, something systematic here in the space weathering results on all of them? But if we start with two different end members, like we tried to start with, we might be able to get somewhere. So I don't have an answer to you yet, but I'm hoping we'll get one if we can do more experiments like this.
Bill, this is Dan, and let me throw my 2 cents in. When you're trying to do remote sensing of, for instance, ordinary chondrites that have been shock blackened, what you do is you're getting olivine, pyroxene, a bunch of metal. And the metal is finely dispersed. If you're looking at weathered uralites, what you're getting is olivine, pyroxene, and finely dispersed, perhaps submicron metal that's been reduced out of the olivines and pyroxenes. So it's really hard to tell that apart.
I was going to say that's the case if you're looking at weathered uralite mantle type material. But if you're looking at a space-weathered piece of uralitic regolith, like in the red sample here on this slide on the right, it's really quite different. There's something else I wanted to mention. I wanted to talk about this, but there wasn't time, and that's it. I anticipated that somebody might say that you could always tell a uralite from a carbonaceous chondrite because uralites won't have a 3-micron band due to silicates, a water of hydration band, and lots of carbonaceous chondrites will. Well, that is actually not true because there are samples of Albedo that contain large, mixed in with uralite material, large amounts of carbonaceous chondrite-like material, C1-like material, similar to what Mike described in the previous talk, and their spectra do show 3-micron bands. So uralitic asteroids can have 3-micron bands on them. I'm sorry I interrupted you, Dan.
Oh, quite all right. I've actually done some experiments on reduction of olivines. And what you do is you get you eliminate the band and you get the very strong red slope. So reduction in formation in nanophase iron is a good path for doing that kind of weathering, and you don't need to necessarily use lasers to get it. It basically is unstable in any reducing environment.
Yeah, that's certainly true, but micrometeorite bombardment over a lot of years will make it worse.
Oh, yeah. It's basically a story of the chemistry and whatever energy input you have.
That makes sense.
Bill, I was going to get back to, and also Mike, I was going to get back to where in this plot that also that you just showed with the chromium versus the other isotopes, or the oxygen isotopes, and the division of the solar system. And it strikes me on the carbonaceous side, you've got this huge variation in basically the water ratio of these guys. And I'm thinking that maybe there are dry parts of that, that the difference between the carbonaceous and the non-carbonaceous material is the frost line. But once you're outside the frost line, there's a big variation in the amount of water that's going into the accretion of these objects. And maybe Jupiter has something to do with that. Speculate?
Well, let me say this, and then maybe Mike will say more. So it's, I mean, so when Mike showed his plot, he said essentially he said there seems like there might be a relationship between how primitive something is and where it is located on that plot. But I noticed that like CM chondrites were pretty low on that plot compared to other things, and that confused me.
Can we bring that plot back up? I know Serena, did you have you had that plot in your talk?
I think she showed it a couple slides ago.
Yeah. Can we bring that back up? There we go.
Oh, one more. There you go. Yeah, so look at CMs down there near CVs and CBs. So they're in a very different part of that plot than, let's say, Orgay and some of the others. So I guess I don't have a feeling for what that relationship, is there a relationship there that means something? I'm not sure.
Okay, I think that's a good point.
I have to let you guys tell me.
Well, in the x-axis there is, for sure, but maybe just not in the y.
Yeah, I don't know what, if you're higher on that plot, what does it mean?
Right.
I mean, maybe there's something, but I think CM and Murchison are
well, the big difference between the CMs and the CRs and the CIs and other stuff is that the CMs are a lot more reduced. So you get a different form of serpentine than in the CRs and the CIs. So you get a much more iron-rich serpentine. And that might have something to do with it.
But the CKs are some of the most oxidized in their way at the bottom. I don't know.
Yeah.
I don't know if they're in terms of the serpentine.
Well, the CKs don't have much serpentine.
I guess if you threw out Ben Cubbin, maybe then there is kind of a relationship. Looking at it.
Well, it's telling us something here. We should pay attention.
Yes, it is telling us something. I agree. All right. Well, so let me take a different. Since we have Serena here, I want to ask about this. So I'm trying to understand urolites, right? So urolites are in the non-carbonaceous part of the plot, yet they're carbon rich, and so I'm trying to think about how one would arrive at something like that in the terrestrial planet region, if this whole scenario works.
Well, there's carbon throughout the solar system.
Yeah, but they're really rich, right? They're like what, like 4% carbon, and build up to 8% carbon, and why are they special compared to all these other things?
Why so much more carbon than you see in the ordinaries?
I don't know, but I I don't know if we need to think about carbon abundance changing with heliocentric systems.
Why not?
I just don't know if we do. Why should we?
I don't know. That's what I'm.
Yeah.
I mean, I don't know if it does, but I'm wondering if it does. So, and at some point, everything has to have a home. So I'm trying to figure out, like what's the home for the Uralites? Where did they grow up?
Well.
So let me ask a completely crazy question, which, since this is what this carbon workshop is good for. So earlier today we talked about how in mercury, if you had a magma ocean byproduct, you might get a graphite-rich residue which would float to the surface, and that would be very, presumably very carbon-rich. And Uralites are a mantle product. Is this something that you might get from? I mean, are those two? I'm not saying the Uralites have to come from something mercury-sized, but does that same relationship hold in some fashion? Is that how you would make Uralites? I'm not saying it very well, but you guys know what I mean?
Can I say something?
Absolutely.
Bill, I think it depends on the style of melt extraction on the parent body. In the case of mercury, they're talking about a magma ocean. The large body of magma, so of course graphite will float in it. But on the Uralite parent body, it's almost certainly the case that melt extraction was fractional melt migration in small veins, and dikes. It could not possibly have had a magma ocean because you had to preserve the oxygen isotope heterogeneity. So in that case, well, we actually did calculations in a paper, Wilson et al. 2008, showing that if you had graphite crystals that are the size of what they are now in Uralites, which is where you would get them to be at around 1200, 1300 C, the peak temperatures, they would have been too large to actually be carried upward in the veins of melt moving. Does that make sense?
I think so.
I think in terms too of for sort of like an analog standpoint, people tend to go towards more the Albrights and the Enstatite chondrites, and even more recently the Enstatite impact glasses, Enstatite chondrite impact glasses, to use those as analogs for Mercurian conditions.
We've got some comments in the chat box. Carly wants to know, can some of the S asteroids be weathered Uralites?
Oh, I'm looking at this.
I think by the plot you show, the answer was yes.
Yes, yeah, I would say so.
The other question in the chat box is, can you explain again why Uralite parent body cannot have a magma ocean?
Yes, although it's hard to explain without the proper diagram, which would be an oxygen isotope diagram. Uralites have another characteristic that distinguishes them from other groups of A chondrites, like the HED meteorites or the Albrights, for example, and that is that their oxygen isotope compositions don't fall on a mass fractionation line, which is a slope 1/2 line on the standard 3 isotope plot. They fall on a slope 1 line, which is the kind of slope line that chondrites and other primitive materials plot along. So the interpretation of that is that they had this heterogeneity, a primitive-like heterogeneity in oxygen isotopes in the precursor material that was not removed by the igneous processing. And that can only happen well, it certainly can't happen in a large body of magma because oxygen moves around very quickly in a melt, and oxygen isotopes re-equilibrate quickly in a melt.
So it's just been a high-grade metamorphism that allowed the crystals to grow.
That's correct, yeah.
Okay. Diane has a question. Are uralites younger? Earlier in the disk evolution, inward accretion migration was more efficient, and maybe that could transport / survive / incorporate more organics. Organics can survive inward where water does not.
I don't know I don't know younger than what. I don't know what the question means, younger than what.
Well, younger than, say, carbonaceous chondrites, for instance. Were they accreted relatively early and sucked up a lot of the interstellar dust and graphite?
Well, the answer to that is, of course, model dependent, but I think so. I do think that they accreted earlier than carbonaceous chondrites. The reason for that comes from thermal modeling, aluminum-26 modeling of what it would take to get to 1300 degrees C on the urolite parent body. And the main constraint is that if you want to get to such a high temperature, you had to have a lot of aluminum-26 around, which means you need a very, very old accretion time, or an old time for the beginning of the melting. And so our result was that urolites accreted between 500,000 years and 1 million years after CAI. But as I said, it's a model.
Okay, and so the carbonaceous chondrites, in contrast, accreted a bit later, or or
later. I'm not an expert on carbonaceous chondrites, but the accretion times for chondrites are 2 to 3 million years after CAI.
So we're talking 2 or 3 half-lives of aluminum-26, which would make a big difference.
Makes a big difference.
Let me get back to Carly's thing about can uralites be from S-class asteroids. And the whole point was, I thought in the plot of the weathered samples that you compared them to D-type asteroids, not S-type, right? Aren't they redder than S-type?
Can we see that plot again?
I'm trying.
Okay.
Oops.
Yeah, and also, I made my comment before, but there's also an albedo issue too. That's going to matter for us.
Oh, yeah, actually, there's a huge albedo issue. Let me go back to the albedo slide. You see, here's the albedo slide. You see where the S's are? They're up here.
Yeah.
Okay, I think we were looking at the plot on the left, which shows those green dots getting pretty close to where S's are.
Yeah, actually, thank you, Bill. That's a good point. The whole reason I added the plot on the right is because that plot on the left is really disturbing because it makes it look like the uralites are going towards the S's. But it's obvious when you look over here on the right that they're getting so much darker than the S's, that the S's are not an option. So I guess I take back the answer that I gave to Carly.
Yeah, that makes more sense.
Thank you, Bill.
Oh, I didn't see the right plot long enough to appreciate this question. So.
Yeah, sorry.
No, it's not your fault.
Actually, Bill, you're going to have to take all the rest of your questions because I need to hang up here.
I think that means we're not taking any more urolite questions.
Well, actually, Bill,
great job.
Bill, I would like to hear your thoughts on where the uralites accreted and why they have so much carbon.
I don't know. I'm very confused.
Reality is like that.
I guess, right, so Amanda suggested that we shouldn't think about this in terms of semi-major axis, but I can't help that. I mean, I'm a semi-major axis guy, right? So
I don't think we should be confused that they have a lot of carbon, even though they might come from bodies inward of where the C-class bodies are.
Well, I think that...
I don't think that should be mysterious.
Well, I mean, I guess where we're at is that if you believe the sort of global scenario that exists, then the non-carbonaceous material form in the inner solar system and the carbonaceous form in the outer solar system.
But everything gets moved around.
Everything gets moved around, but they're where they start are those locations, and then they move around. Okay, so I don't think you can make Uralites in the outer solar system because that would put them on a different part of the Warren plots, as they so call them. So then I guess the only thing I can think of is if carbon. Okay, if the source of carbon is the outer solar system, then I think the easiest place to make the Uralites would be the closest place to where that carbon is, if that makes sense. But that might be a completely wrong way to think about it. But that's as far as my thinking goes. So
well, but there's another factor in here, and that's time. And if you're 2 or 3 half-lives of aluminum-26 earlier in formation, then you're sampling a different solar system.
it's true, and maybe they form before Jupiter reaches its full size, and so maybe there's more room for fun with carbon in, you know, I mean, okay, so, all right, this is just wild speculation, so no one should take any of this too seriously, but, I mean, there's some interesting models that suggest that possibly all the carbonaceous chondrites were put into the asteroid belt, but also maybe almost everything else was put into the asteroid belt from the inside. So the question is there anything that's actually indigenous to the asteroid belt? Okay, and so if I had to, like, but based on this conversation and things I've been wondering, I've been, could Uralites be indigenous to the asteroid belt region? Because that asteroid belt region is the closest we would have to a carbon-rich region. And so if carbon was intrinsic, then that's sort of the way you could go. So like the further you get away from Jupiter, the more likely you are to be low in carbon, I think. But you know, is that but maybe I'm just trying to connect dots that shouldn't be connected together. That's about as far as my thinking goes on this. It's also weird because the Uralites are a mantle product, and so is that somehow mixing up the issue?
Right.
You know, we're trying to treat them like everything else, but they're not like everything else. So.
Yeah, it just amazes me that so much what is essentially pre-solar material and graphite survives in Uralites. And the kind of the baseline level of carbon in all the other anhydrous meteorites is, you know, a few tenths of a percent up to 1%, and then you have a factor of 4 to 8 higher in Uralites, and it's disturbing. So it might very well be time, but I just don't see how time helps all that much. Unless we don't, you know, there's fundamental.
You're talking about distributions of carbon in the solar system, so.
But I don't know what to think. I haven't formulated a hypothesis here yet, but I do think that mantle material changes things a lot.
Yeah.
Well, but it's not mantle in terms of a differentiated planet mantle. It's mantle in terms of basically high metamorphic grade stuff.
What's the difference between those two?
Well, one melts and the other one just gets warm and fuzzy and soft and fuzzy.
But I thought that Serena said that the Uralite parent body was differentiated.
No, I think she said it was just high metamorphic grade.
No. I didn't check my notes. But I think I wrote down different. I have it. I have it. Well, okay. For my notes in her talk, she says she was talking about carbon, and then she talked about it's a mantle byproduct, and I think somewhere in there she said differentiated. It's probably the beginning of her talk if we go back to her slides.
Okay.
She either said that verbally, but you know, of course.
She said differentiated. I wrote differentiated.
Okay.
All right. Well, I'm not a Uralite person, but I did ask her about that, and she said something to the effect about high metamorphic grade.
Well, that's where I don't understand.
So my thinking about the distribution of carbon in the solar system, I am wanting to get a better grasp hopefully from this workshop, on how meteorites might fit into all of it. Because I think it makes sense in my mind with the objects in the solar system that we're looking at. Trying to figure out where the meteorites actually came from is a little different thing in the whole sort of carbon continuum concept.
But you also have, so you're interested in kind of the distribution of organics and what they look like when they started, right? But
Yeah.
then you also have this parent body processing going on, and it's kind of up for debate how much that's changing the organics. You have a whole other layer on top of that, it feels like.
Yeah. No, there's definitely a few things going on.
Carly writes, if S asteroids can be raylights or ordinary chondrites, that makes a big difference for models in the inner solar system. Somebody needs to find a way of distinguishing the two, and I think we've done that. It's albedo. So identifying a raylight parent body just needs spectra and albedo measurements. I think that's true. Diane Wooden writes, speculating about time. Time may give the result of multiple processing events, like chondral forming events, wherein heating experiments show carbon can be transformed and lost as CO and CO2. Influx of outer carbon-rich material is slowing or choked off by Jupiter ?
Well, okay, let me take I mean, there's a lot there. Let me take a stab at least one part of it. At least this is sort of what I'm thinking. So imagine you're in a solar system before Jupiter's reached its full size. So then you probably have a lot of carbon-rich material from the outer solar system, which is trying to move inward. It's trying to migrate in. Okay, and it reaches some point where, you know, the glue that's holding the carbon together loses its ice and it goes away. But it's still, I've always wondered, well, what happens to all those grains? Do they all just go into the sun, or do they get caught up in other things going on? And so I've always, you know, so in that vein, like the place where you're losing, where the ice is going away, but you're keeping the carbon, is that the place where the Uralites form? I think that's what she's getting at, and that's kind of that's kind of what my thinking is. But I think again, it's simplistic because I don't understand the Uralites entirely.
I think you have a lot of company there.
Yeah. In terms of the rest of her comments, I don't know if I can say anything useful.
Well, Diane writes, I was thinking about how time could change the carbon abundance with distance. And I think that's a reasonable supposition, is that to some extent the nebula is reprocessing and replenishing things like water, ices and of various sorts, and certainly chondrules. But maybe there's just a finite supply of pre-solar carbon, and that goes away fast. Gets incorporated into stuff.
But who gets it?
Well, basically we've got all the meteorites have a little bit of it. But I don't know, it's just that the raylites and the carbonaceous chondrites have more, or the volatile-rich carbonaceous chondrites. And so this is being scavenged out of the nebula by some process, which I don't understand. Do we have another? We've been focusing on raylights for quite a while. Do we want to try talking about a few of the other topics that we were dealing with? Unfortunately, is Mike still on?
I think Mike had to go.
Okay.
I think there was an LPI comment above that said they think Mike had to leave, but
Okay.
I could probably say a few useful things on that if questions come up. But
Okay. Well, I was just wanting to speculate a little bit about the regolith brooches and the things he's founded in these various random meteorites. So
Yeah.
perhaps you would like to hold forth on that?
Well, I'll do this. I'll tell it in the form of a story. Right?
Okay.
So, just much more easy to tell.
Gather around.
Yeah, everybody, gather around the campfire and we'll tell a story. No, so a couple of months ago, before LPSC, we were writing LPSC abstracts. Mike contacted me, and he told me about this ZAG class that they had found. And he said, this looks, effectively very much like, he was telling me about the halite and the rest. He was telling me this looks like something from, I don't remember exactly what he said, but something that looks very cometary. And he said, well, I think this might be from Ceres. And I was unhappy with that because it's not clear to me exactly how Ceres stuff would get there. But it's not impossible, but, I didn't think it was necessarily the only possibility. But the more you described it, the more it sounded a lot like the kind of material that would be, things we would find in the outer solar system. And we had published a paper where we suggested ways to get things into the asteroid belt, particularly from the Kuiper belt. And we have a paper published on this, and the model looks really good for injecting material from the Kuiper belt into the asteroid belt. And they would make, the P and D type asteroids we see there would be from that. So if that's true, then I think you would have a lot of ways to put P and D type material into the surfaces of a lot of bodies. So the fact that he's seeing this may even be evidence that this had to take place. So the timing of what he gets in some things should be really interesting. I guess the question is, are there other ways to put that material there? Do you have to? A lot of our micrometeorites are probably from comets. I think this stuff may be bigger than what we get from most micrometeorites, but I'm not sure. So that would be a Mike question. I was mostly interested about it, or what he hadn't showed me before was the oxygen isotope diagram showing this guy is way different. It's a very different place than the other carbonaceous class we've seen. It's above the terrestrial fractionation line, yet it follows the CAI line. That was cool. What does that mean? Does anyone know?
I don't know.
It was between TF and the CCAN line.
No, right. You know how the terrestrial fractionation line has like one slope, and then there's another carbonaceous line. They kind of meet like a triangle.
Yep.
If you take the carbonaceous line and you keep extending it, it was above the terrestrial fractionation line.
So it would have been along the CCAN line.
Yeah, it was along it, but higher than the terrestrial fractionation line.
Right. Yeah.
And I hadn't seen that ever before, which was really interesting.
Yeah, I think the compass complex type is along that.
I can explain the series origin a little bit more. The reason why we started looking at series, basically okay, so started back with the H chondrites. Apparently the predominant candidate as the parent body for the H chondrites right now is asteroid Hebe, and went looking at the orbit of Hebe, and turned out it basically has a crossing orbit with Ceres. So there's points in the orbit where material could be transferred from Ceres to Hebe with delta V at the receiving end down in the hundreds of meters per second, maybe less. And that would be necessary to make for the survival of these halite grains. Not only did they survive, but they were never heated significantly. They still have fluid inclusions inside of them. So whatever happened, they had to transport themselves very gently onto the other body, and they are up to centimeters in size. So it's not like little floating snowflakes or anything.
Yeah, I guess what I would say on that, I don't remember what I said to Mike, but it's so what happens is if you have a collision, let's say, anywhere in the asteroid belt, and you create centimeter size or smaller fragments, even centimeter size guys are large enough to evolve by Porting-Robertson drag, they just do it more slowly. So they're going to start to evolve inward, And so some of those bodies, as they evolve inward, are going to match course and speed with different asteroids. So they may be able to land at low velocities. So I don't necessarily think you need series. You just need stuff, right? And so I think a lot of things in the asteroid belt can land on each other if they're small enough and Poynting-Robertson drag can do its thing.
Yeah. Yeah, that's a good point. I think one thing.
Let me say this: it could be series. I have no reason. I don't know why series would win the battle against everybody else, but it could be series. I think it's hard.
Could be series. Could be something like series. Basically the things we came down to were that the orbital dynamics thing. Also, we're seeing a surviving population of what must have been. This is much more. This is speculative, but in order to have surviving 4.5 billion year old halite now and keep finding it in these two different meteorites, it probably was quite a large volume of material back in its day. So that kind of hints that wherever it came from, it was quite voluminous, especially if it was like you were saying, it was basically getting scattered through the volume of the asteroid belt and swept up by other asteroids. The other thing is actually from the carbon itself in these inclusions. Part of the Raman analysis was amounted to trying to. You don't really classify them as carbonaceous chondrites from different carbonaceous chondrites from their structure, but you can classify them as being, say, CM-like, CV-like, CK-like, CI-like, whatever. And the material in these inclusions falls into three separate types of material. There's some CV-like material, most of it is CM-like, and some of it looks like shocked graphite. So that kind of implies you're getting material from multiple sources, which in turn implies that whatever is the source body of this was something large, able to sweep up material from multiple originators. And there's a lot of speculation with this. That's why we kind of say, it could be series, but whatever it was wet and it was big and it was carbonaceous is what we're thinking.
So that if I can follow up, because
sure.
If the stuff looks like, all right, so it actually, I think, matters if it looks like CM or CV versus, let's say, it looks like CI or like CK or CI or CR or something. Like right. if it's super primitive, that points to one sort of suite of models. If it's a little bit more evolved and less primitive, that points to another suite of models. So I'd be really interested to know what you guys think of those things. Like, because P and D type asteroids, I would think should be really primitive stuff. And I don't think CV is. I wouldn't call CV stuff primitive stuff.
Oh no, CV has been heated to like 400 Celsius or so.
Yeah. So anyway, I mean, that composition matters, and we could do stuff with that, trying to figure out dynamically what it would mean and when it would happen. I mean, so I could. This is from a limited.
This is from. What are we at? About a dozen different grades now. There's more material we can look at. If I could get some more time and look at more material, I think we could flesh out the total population of the carbon a little better. Comes down to instrument time. Yeah, well, I can say this much. It's mostly CM-like. There was actually the CV-like material was in one grain only. And the shocked graphite shows up in several places.
And the size of the guys we're talking about here. All right, so there's two things, right? So, like I say, I was on Alan Rubin and Alan came to me and he had some eucrites which had CM class, which were still had phyllosilicates, and he also found the same thing on H chondrites, and they were pretty big class. And the impression I got from Mike is that the things that you guys are finding now are smaller and are different from those. Is that true?
Oh, the inclusions in the halite, oh yeah, they're tiny. We're talking like, maybe 100 microns. Are
they different? Are they essentially different composition than the big things, the big class in eucrites and rest? Mike sees similarities with the
with his unusual class there is from ZAG. Basically, you know, the same meteorite that has some of the halite in it has this big carbonaceous class that's it's at least millimeters. I think it's about a centimeter in size. That's what he was showing all those the data along this the CCAM line that, you know, like you were saying, runs way north of the terrestrial fractionation line and such.
Right.
His conclusion there is that this is the same material as what we're seeing, same or very similar material to what we're seeing trapped in the halite.
Okay. Yeah, I mean, well, we should, I'm worried we're getting in the weeds. I'm looking around the room and everyone's kind of looking at,
Okay, sorry.
Probably it may be about time to wrap this up for the evening at least. But think about questions and we can get back to all of this tomorrow or Friday.
Can I make just one quick kind of general observation from the talk today?
Sure.
I'll be brief, but see, one of my takeaways is that there's kind of there's a nomenclature problem.
That's new?
No, actually, that's kind of the thing. You know, studies of carbon span a whole bunch of different communities: petrochemical, terrestrial geology, astromaterials, etc. And everyone has their own meanings for things. For example, I heard a few people call things kerogen today. In terrestrial geology and astrobiology, kerogen is any macromolecular solid that originates from formerly living material. Which is why the astrobiologists have become very leery about using that term. Another one is graphitization. From a mineralogical standpoint, you know, if you're graphitizing, you are making graphite. Graphite is a high temperature single crystal thing, and that kind of implies that you are dealing with temperatures of like 1500 Celsius and higher. So I'm just pointing out that there's a wide range of different terminology being used, and maybe a collectively agreed upon glossary would be a good step moving forward.
One good product. Yeah. I like it.
Well, a lot of the organic material that we're talking about, especially things like PAWs, are chemically kerogens. Unfortunately, the whole kerogen terminology is dominated by the oil industry, which cares about fossilized, insoluble organic materials. Even though you're talking the same chemistry, because PAWs are basically type 4 kerogens.
True, but in our case, they're not biologically derived. I prefer the term.
Yeah,
basically, I use the term macromolecular carbon.
Yeah, but the problem is that the whole biological thing is a red herring. It's just a holdover from petroleum geology terminology. And I frankly can spell kerogen a lot better than I can spell macromolecular carbon.
I think it's okay to use the term kerogen-like when describing some of the stuff, like comparing D-class asteroids and stuff.
You know, the soil scientists regularly berate us for calling it soil because they say soils have organic material in it that's derived from living processes, and we have successfully ignored them all my career in planetary science.
Okay, good. So let's all be thinking tonight over dinner and whatnot about other kind of larger issues that we want to discuss tomorrow and on Friday and at future workshops, and what you might think might be, you know, themes of other workshops. And the other thing is I'll bring up is that, and I don't think we've brought this up yet, Faith, is that we want to have a second workshop, but we also want to maybe have sub-workshops between now and the next one. Maybe a special AGU session. Maybe a workshop on the Sunday before DPS starts.
Right.
Or, you know, those types of things. Like, breakouts from this, maybe focusing on some particular theme, to move the discussion along. So think about that also. Okay.
Okay, so we're wrapping up for today.
Yes, I
We're
think
wrapping
so.
up for
Thanks,
today.
Dan. Thanks for
Thank
being
you.
with us
Thank
this afternoon.
Thank you, Dan. Thank you, everybody who spoke and everybody who questioned everything. Appreciate it. And helped me get online, too.
We'll start at 8
Thanks, y'all.
a.m. Pacific, sharp tomorrow.
Okay.
All right.
We'll see you
Bye.
then.
Okay. Good night.